Hello, this is the fifth FRQ of the Unit 11 project. So let's get into it. So we're doing with a capacitor. We're going to need to know that uh, equivalent resistance is going to determine battery voltage. Steady state would be after a long time. And then the switch opens. We're going to need to know that when the switch opens, the capacitor is going to discharge exponentially. So those are our physics facts, and then some relevant equations. And then also we rearrange that for V equals R. We need to know that Q equals C times voltage of the capacitor, and then also that potential energy of the capacitor is going to be that. So, with that being said, let's get into it. So, drawn expression, steady state current supplied by the battery. So, the capacitor, so the right 2R is going to carry no current because the capacitor is acting as an open circuit. So then the battery is just going to see this 2R plus R. So it's going to be I battery equals V naught. And our equivalent resistance in series is just R1 plus R2, which would be 3R. That's A. Derive an expression for the charge on the capacitor. Well, we know the right branch, this is series, it's R plus 2R is 3R across V naught, so our currents, I equals V naught over 3R. The voltage across bottom 2R, or so the voltage across the capacitor is going to be the voltage across the capacitor will be, that would be I times 2R, because we have V equals I times R. So it's going to be V equals I times 2R. And then since we've calculated I to be V naught over 3R, that'll cancel. So we get 2 V naught over 3 for our voltage. And then we just have to plug this into our Q equals C. It's voltage capacitor formula. So it's going to be 2C V naught over 3. That's our expression. Derive an expression for the energy stored in the capacitor. Well, we have this equation. Oops. Sorry about that. And then we're going to 1/2 C 2V0 over 3 squared, because that's what we got for our VC previously. So then we're going to get 1/2 C. It's 4V0 squared over 9. That's going to be 2. And that's going to be our expression. Energy stored in the capacitor. Because energy storage is just another word for potential energy. Write but do not solve a differential equation. Well, for this, you need to know that I over dt and the capacitor would discharge through R plus 2R equals 3R. So, and Q equals CV. CV and V. So what we have here, we're going to use for the switch open Kirchhoff's loop rule. And we know it has to equal 0. So our two voltages, we're going to have Q over C. And then that voltage would be dq over dt times 3R. So we're going to have Q over C. We're going to have Q over C equals 3R Q over QT. And then we would rearrange and we'd move this Q to be with dq over dq. We'd get the R and the C on the same size, and then that would be our differential equation. Evaluate the current immediately after the switch is open. So immediately after the switch is open, that would be immediate. That becomes so after a long time, it would end up approaching 0 with the exponential decay, but immediately after, it would be that voltage of it would be current. Well, it would then be what we calculated above, which was 2V0 over 9R. V0 over 9R. Explicitly label the maxima with numerical values. Okay, well, we know it's going to be starting at the max. 2V0 over 9R. and then it's gonna exponentially decay. So in our equation is going to be e to for 3 RC. So and then that's going to exponentially decay. Oops. And it would look something. Ugh, sorry about that. It would look something like that. Oops. I can't draw it well on the computer, but you get the idea. It would exponentially get smaller and smaller, and then it would approach 0. It has a horizontal asymptote. 0. Is the total amount of energy dissipated in the resistors at this visual point less than or equal to in part C? Well, in part C we calculated 2C V naught over 9, and so this would be, I guess, law of conservation of energy. So after it's the total amount dissipated would be equal to what we got in part C of 2C V naught squared over 9. Yeah, so it would be equal to. That's how I justify it. Law of conservation of energy. Okay, well, that's everything, and I'll see you in the next one.